Okay, so it's a pleasure to introduce the next speaker, Jacob Bourjaily from Penn State. So over to you, Jacob.
Yeah. Well, thank you very much for including me in this very interesting dialogue. I've really enjoyed the first couple days of talks, and I wish we could all be in person so I could spend time with old friends and make new ones. My talk today is I took the request for a colloquium level to heart, and so I wanted to give you a big picture view of some of the general structures that we've been exploring in quantum field theory, how they arise, and in particular the Calabi-Yau geometry, how that comes about, and some of the big picture philosophy about how we're going about exploring and improving this today and in the last few years. So I should apologize in advance that this talk will be very high level, but I hope that's okay. I'm happy to fill in as many details as anybody's interested in asking about as we go. But I thought that it would be a good idea just to kind of step back and ask some really simple questions that it seems like nobody or doesn't seem to be asked very often. For example, I know there's a lot of mathematicians in the audience, and a natural question that seems to have been asked or infrequently asked is a very simple one. What is the mathematical form of the predictions that come out of quantum field theory, perturbatively say? I mean, we all know that non-perturbatively there are Airy functions and all sorts of complicated things. But when all the dust settles and we get down to a final prediction, what kinds of functions come out? What is the vocabulary of functions? And this played this question and the kinds of answers to it have played a big role in a lot of the progress that Mark described yesterday, and Anastasia as well. And I'm very happy to have been following both of them in this talk. But anyway, this is a question that we can answer by looking at data, just like Anastasia said. We can take a very phenomenological attitude. And unfortunately, and as I hope to emphasize in this talk, there is relatively little data, and that the data that is very well understood is extremely narrow and extremely limited. And so answers to this general question have been hard to come by because of the want of data. And so I wanted to start with three simple examples of perturbation theory that has been pushed pretty far. And I'm going to start with the most classic example that anybody knows about in a quantum field theory course, which is the gyromagnetic ratio of the electron. This is something that we all learn in a quantum field theory class and compute to one loop by, in homework or something. And famously, of course, the leading order, there's a single Feynman diagram, and it gives you a gyromagnetic ratio of 2. You could say that's what got Dirac his Nobel Prize in some sense. And at one loop, there's a single Feynman graph. And usually students spend an entire week doing numerator algebra to get an integral that is very hard until you learn new tricks. And that when all the dust settles, the answer is 1. It's a very complicated way of writing 1. I think it should be more embarrassing to us as a community that we get numbers so simple. At 2 loops and beyond, you really need computers, or at least heroic efforts. And even though there's only 7 Feynman diagrams, they're very hard to do. And I'm actually not sure that Peterman got this correct in 1957, and he certainly didn't get to 50 digits. But one attitude would be, an attitude by a lot of phenomenologically minded, real phenomenology minded theorists, is a number is good enough. And so let's just get digits out of the machine, out of these things. And if you do that, you get something like this. But my talk is not about the numbers that come out of quantum field theory. I want to know the form, the structure. And so a much prettier and more elegant way, I think everybody would agree, to write this same expression is in terms of this, which I'm not actually sure who originally wrote it to this infinite precision, but I know about it from Laporta's work. And you'll notice some interesting structures. So first, there's this kind of zeta is the polylogarithm. This is in case the Li3 evaluated at the number 1. Log is log. Pi squared is pi squared. So zeta 2 is like pi squared over 6. And so you can see that there's kind of a tower of weight, of transcendental weight, which is powers of pi, roughly speaking. You can see there's a weight 3, this is weight 2 times weight 1, so that's weight 3. Zeta 2 is weight 2, and then rational. So we have this nice structure here. Now, whether or not you want to say that these numbers are simple or not, I just want to point out that there's a nice pattern here. The pushing this to 3 loops took actually, it really did require modern computers, or at least computers in the last 20, 30 years. It was first worked out in 1990, and I'm pretty sure also not to 50 digits by Kinoshita. And it was recently brought into infinite precision, again, by Laporta more recently, and it's this expression. Now, there are a few things to notice I want to draw your attention to. So there are more zeta values, these like, numbers like powers of pi. Then there's this unusual thing, U31, which is a linear combinations of pi squareds and Li4 evaluated at half, and log 2. There's a nice expression, but this, fits on one line. And again, whether or not you see this from the 87 Feynman diagrams, I believe, 72 Feynman diagrams at 3 loops, I'm not sure, but you can see there's this kind of nice pattern. And you might wonder, how far does this go? And of course, it becomes increasingly hard. At 4 loops orders, we're talking about 891 Feynman diagrams. Well, it turns out that doing 4 loops, those 891 Feynman diagrams, which nobody does, by the way, you group them into gauge invariant subsets, is actually not a computational challenge. I mean, at least it's not anymore. Laporta has computed this to, I think, tens of thousands of digits. At least in the literature, it's printed to over 1,000 digits, which really means that it's a number that is known to infinite precision. Essentially arbitrary precision. But there's no analytic expression that's known. And there's a very interesting reason why that I'm going to come back to in a little bit, but I'll just to foreshadow slightly, there is exactly one integral that you need at 4 loops that does not fit into the category of numbers that have nice names. Laporta calls it a triple elliptic integral. And it happens, and I think another way of, an equivalent way of saying is that it's the period of a Calabi-Yau threefold. And unlike the zeta values or multi-zeta values or these kinds of classically, familiar numbers, this one just doesn't have a name. So it's been computed to many, many, many digits, hoping that somebody decides to give it a name. But that's why I can't write it out to 4 loops. And at 5 loops, it's only been done numerically. But so anyway, the themes here are that there's this nice kind of structure pattern, but I don't think anybody expected from the first 3 loop orders that there would be these weirder numbers starting to appear, although hints of it might have already been there. The next example I want to pull from is probably from the nicest possible quantum field theory that Mark and Anastasia talked about yesterday, which is planar, maximally supersymmetric Yang-Mills theory in the planar limit. Arguably, at least by most modern practitioners, the simplest quantum field theory we could possibly work with. And there's exactly one observable, well, I should point out, one problem with going to a nice theory like Yang-Mills that is not there in G-2 is that theories of massless particles have infrared divergences. So a simple amplitude just doesn't mean anything. Instead, you have to talk about finite observables or observable related quantities or something finite, something that's scheme independent to talk about. And those are a little bit harder to construct and a little bit harder to organize. And so the first, or at least maybe the best known example of a finite quantity in maximally supersymmetric Yang-Mills theory in the planar limit is for 2-to-2 scattering. And this is a divergent amplitude. But it's the coefficient of the leading divergence of the log. It's called the Cusp anomalous dimension, and it is known essentially to all loop orders. And it has a very beautiful structure, much prettier than I think the G-2. Although again, we're just talking about numbers here. Yeah, I'm going to talk about functions in a moment. But you'll notice that at 1 loop, it's the number 1. At 2 loops, zeta 2, zeta 4. So the weight is 2 and then 4 and then zeta 2 cubed. So that's 6, 6, 6, 6. Everything is weight 6 at 4 loops, 5 loops, it's weight 8. So it's uniformly transcendental all across the board. And this feature, I should have made this alternating, but I'm just imagining an imaginary coupling constant. It doesn't matter for the purpose of this talk. And you might wonder, is it possible that you can write it as a positive sum of products of zetas, simple zeta values, not even mixed, not even multi-zeta values, but just simple, the nth polylogarithm evaluated at 1, the classical zeta value, can you write it that way with positive integer coefficients? And the answer is yes, to all orders, which is a rather pretty result. And it's one of the bits of data that led people to suggest, and it is a conjecture which has already evolved in its meaning several times, but it has led to the conjecture that maybe this particular quantum field theory in 4 dimensions is not only transcendental of predictable weight, but that it's uniformly so, and that it is maximal transcendentality. This is the most that any Feynman integral can have, and that n equals 4 should be the nice theory that lives only at this maximal transcendental weight. As we'll see, the meaning of this, so as I hope some of the mathematicians in the audience are squirming a little bit, transcendentality is a very delicate term. You might say weight, at least that's well defined on this slide, but we'll see that it quickly becomes less well defined as we actually start probing n equals 4. But anyway, this idea that you'd get every amplitude or at every observable at a certain loop order would be constructed out of functions that have maximal transcendental weight has been a conjecture, an idea floating around for many, many years. And I'm putting a question mark on it because I do think this is true. I just don't think it's means what anybody thinks it means, or at least not until very recently. It keeps changing. The problem with a theory of massless particles, of course, is that the infrared divergences force you to talk about finite quantities that are somehow, maybe ratios of amplitudes are infrared safe. And those are harder to compute. Not only are they not numbers anymore, but they involve all the dependence on the kinematic data, all the momenta and the Mandelstam variables that you can have. And so it really becomes a truly difficult job to calculate even the simplest possible finite function, finite observable that's not a number in any quantum field theory in 4 dimensions beyond 1 loop, I should say. 1 loop is a little bit too easy. And the first example of such an observable, which stood as like a challenge to the community for a long time, not anymore, of course, is 2 to 4 scattering at 2 loop order. And again, this amplitude is divergent, so you have to define something that's computable, and you compute this, what's called the remainder function, relative to the divergences. Anyway, it doesn't matter. It's something you can compute, it's finite, it's something. And the Feynman diagram representation of this thing has been known for a long time, or had been known for a long time, and something like a straightforward problem of just regulating all of these integrals, adding them all up, canceling all the divergences, and seeing what you get. And this was done through truly heroic efforts by Del Duca, Duran, Smirnov in 2010, just a little over 10 years ago. And along the way, they introduced physicists to a broader class of functions. They learned that they couldn't just write polylogs, for example. They needed a bigger class, or at least they thought they did, of functions that they called Goncharov polylogarithms. And so they had this paper is like 120 pages of new techniques and ideas and mathematical foundations, followed by the answer. And conveniently, they attached it as a Mathematica file because the actual answer they published is 18 pages that you cannot read of little g with 4 arguments, Goncharov polylogarithms. And these Goncharov polylogarithms are also just called polylogarithms or hyperlogarithms or whatever. They're just iterated polylogarithmic integrals that Mark talked about yesterday. And famously, Mark and Anastasia and one of their postdocs, Christian Vergu, teamed up with Sasha Goncharov to analyze this 18-page formula and quickly discovered that first, you don't need Goncharov polylogs. You can get away with classical ones. And that entire 18-page expression fits onto 2 lines or 1 line if you printed it in a paper. And this degree of like shocking simplicity really was, it was a mystery at first, and then it led to the developments related to some symbol alphabets and eventually to cluster algebras and all the other things that we've heard about already in this in this conference. And it has been pushed to industrial scale efforts, I believe it's safe to say. In the last couple of years, this particular calculation has been pushed to 7 loops. And it was not done the old-fashioned way by calculating divergent integrals and canceling things. No, this was done at 7 loops. I know I'm writing only Dixon here, but there were a lot of people involved in it. But it was done using the ideas of studying the argument space of these polylogarithms and using that to iteratively bootstrap. I know Anastasia talked about this yesterday. And this has been quite a triumph. And you get these nice things. And it is indeed true that at L loops, these observables in n equals 4 are weight 2L polylogarithms, at least through 7 loops. Yeah, and that's really the limits of our understanding of like high order calculations. At 1 loop, we kind of know everything, and at 2 loops, there are very few isolated examples that have been studied well, and a relatively small list of actual observables that have been computed in a form that's not numeric, that theorists like me can stare at and learn something from. But an interesting question, going back to this, what kind of mathematical form, I think that if you would have polled people, I'm not completely sure, but at least, say 10 years ago, well, how long would you have to go? 5 years ago or so, you would have asked, what functional form comes out of a general calculation in quantum field theory? And just for the sake of some indices, I'm going to say 4D. I'll show you how to change that in a second. Anyway, every quantum field theory at tree level is just a sum of Feynman diagrams. They are rational functions with simple poles that we understand very well. So we have a rational function always at leading order. What about at 1 loop? Well, in 4 dimensions at least, you get this tower of transcendental weights that weight 2 polylogs, which are dilogarithms. You get logarithms and pi's and log 2s and stuff like that. That's what weight 1 polylogs mean, and rational. So it's a set of those kinds of functions with, actually in this case, algebraic coefficients, but still, these are the building blocks of functions. And I didn't have time to talk really much about in detail, but you can prove that this is true in every quantum field theory at 1 loop. Every single Feynman integral at 1 loop in any number of dimensions. So the general dimension form is to replace 2 in these formulas with floor of d over 2. Anyway, if you do this in any number of dimensions, any 1 loop amplitude is always a polylog. And we can construct them even with masses, no matter what is going on. This is a very general statement that at 1 loop, everything's polylogs. And unfortunately, 1 loop is best, well, not unfortunately, but anyway, it's not so surprising that 1 loop is the best understood order perturbation theory because it's the simplest. And there are so few examples at 2 loops that, and the examples that we have had have suggested that perhaps at 2 loops, you get weight 4 polylogs all the way down to rational. And there are a few observables for the LHC that have been computed exactly like this. And it kind of led to a natural kind of prediction that maybe all you get from perturbation theory in a general quantum field theory is a bunch of polylogs of different weights, and you get this kind of towering structure. There. What are the coefficients? Now, I haven't talked about the coefficients yet too much, but they are weight 0. I would have been, a few months ago, I would have been less careful and said that they were algebraic or even rational. But now we know that that's a little bit too generous, but they are weight 0. And so but they are on-shell gauge invariant objects, and they fall into the category, or at least the recently expanded category, of what are called leading singularities. So they're tree amplitudes glued together on-shell particle exchange, integrated over some contour of integration. The reason why I call them weight zero and not algebraic is because we have plenty of examples now where the coefficients are those kinds of functions times the ratios of complete elliptic integrals, say. So there's a broader class of things. You need to talk about the pies and stuff. And I know ratios of transcendental numbers is even a scarier category than transcendental numbers to begin with. But at least to a physicist definition of weight, I would say that they're weightless coefficients that are built in a very specific and well understood way in any quantum field theory out of tree amplitudes. So n equals 4. So the idea that maximal transcendentalities, that an amplitude, or at least any observable built out of an amplitude, would live in that the nicest possible quantum field theory in 4 dimensions, planar maximum supersymmetry, would live inside this top slice of maximal weight. And I do believe that's kind of true, but at least the arguments about what we mean by weight 4 has to go into an even further tenuous direction mathematically, because it turns out that polylogs are far from the right answer most of the time, and in a way that I'll clarify for you. So it turns out, and we've learned, and this is what I'm going to talk about, that polylogs are a set of measure 0 in terms of this space. Well, we need to go back to the drawing board and ask the question, what are scattering amplitudes functionally? And we learned this by understanding a few pesky counterexamples. So I want to talk about some of those. And it's a little hard to actually go back in time. I've looked through the literature to find the earliest references to these kinds of pesky counterexamples. But most often when they were mentioned at all, they were, or the graphs I'm about to draw were drawn, they were mentioned in the context of something that was really hard. So Feynman integrals historically fell into 2 categories: the ones that were polylogs and ones that were too hard to do. And it's a little sad that they were just left aside or left on the workbench, because there's some really beautiful structure here, and this is one of the things I want to talk about. But unquestionably, the best studied example are these sunrise integrals, which are defined in 2 dimensions, or you can take them as a coefficient of a divergence in 4 dimensions. It doesn't make a difference. But these very simple integrals, and this is probably the simplest integral you could give. You could give it to a graduate student easily and ask them to do it. And if all the propagators are massive, what you get is an elliptic logarithm. And there have probably been a couple hundred papers on this integral and the chain I'm about to talk about in the last couple of years, because it's been a very rich subject of our understanding of quantum field theory in general. But so you have all these masses. As soon as you lose a mass, if any single propagator is massless, it's just a dialog again. So this is an elliptic log or a dialog, depending on some of these mass parameters. If you go to 3 loops, you find a K3 integral. And I also don't know when it was recognized that it was a K3, but it is. And at 4 loops, you find a Calabi-Yau threefold. And so we might as well just call them all this. An elliptic curve is a Calabi-Yau one-fold. So we see this kind of natural thing. There's a Calabi-Yau one-fold, two-fold, threefold. This is an infinite tower of L-loop integrals that immediately give you Calabi-Yaus. And there was a beautiful paper recently by Chuck Doran and his collaborators in 2019, where you show that they're also elliptically fibered, and there's a beautiful recursion for their evaluations. So you can compute these periods. There's a nice mirror symmetry story, all sorts of things that I wish I had more time to talk about. But so this is a very well-studied class of examples, not obviously relevant to n equals 4 or anything, or the standard model with all these masses in it. Because after all, we're talking about 2-dimensional massive theories. And you might hope that, oh, well, perhaps this n equals 4 can get away from this because it's so different from a massive theory in 2 dimensions. Or at least I can define a nice theory without these kinds of pollutions. But I will point out that this is the 4-loop graph that contributes to the electron G-2. And this particular number that you get out of it, which is a period integral, of this, it ends up being mass independence, an equal mass case, it's on threshold, is the number that is preventing us from writing an analytic expression for the for loop G minus 2. That is exactly what Laporta calculated. So you might wonder, well, maybe this is just about massive theories, and massive theories, after all, are terrible. We all hate massive theories. Maybe, you know, do you see anything different in massless theories? And from a mathematical point of view, it's always been for, well, I don't know, at least among number theorists, there's always been a great deal of interest in these kinds of numbers that come out of perturbation theory when they're just numbers, especially, you know, especially if you're a number theorist, that sounds more exciting to you. And there was a conjecture by Kontsevich that, at least in 5-4 theory, that as far as you went in perturbation theory, no matter what you got, you'd always find multiple zeta values, just like these polylogarithms, or maybe this U31 kind of number, those kinds of numbers. And that conjecture was put to rest in 2011 by Brown and Oliver Schnetz, where they constructed a counterexample. Happens at 8 loops. So this is a complete 5-4, it's a vacuum graph in 5-4 theory. So it's a coefficient of a divergence that you would need in the renormalization for 5-4 theory. It's, you know, a little bit removed from phenomenological concern. But it happens at 8 loops. And if you're worried that it's non-planar, there's a 9-loop planar example that they gave as well. So even in most people, many people's, at least your grandparents' favorite quantum field theory, 5-4 theory in 4 dimensions, there are Calabi-Yaus sitting around. And it's a little surprising to me. I mean, I think it's mostly because Francis is well, I don't know, I don't want to put him in a box, but he's more of a number theorist. And functions are more scary as a class of things, you know, functions of many variables as opposed to numbers, which are functions evaluated somewhere. And so I was a little surprised that it happened so late at 8 loops, because there were lower lying examples sitting around even in 5-4 theory. So this diagram here is this double box integral, and it's been known for many years, I guess, that it's elliptic. Whether or not it was relevant to amplitudes is like a longer, more involved story. And a couple of years ago, with Mark Spradlin and my collaborator, well, my postdocs, we wrote a very nice, clean analytic expression for this integral. And the corners here can just be viewed as pairs of massless legs in 5-4 theory. So this is a simple 2-loop diagram in massless 5-4 theory. It involves 10 external particles. So, you know, that's probably why people didn't see it. But this thing is an elliptic trilogarithm, in fact. And subsequent to this this work, we started looking around for more counterexamples. And we quickly led to another infinite category, very similar to the one of the sunrise integrals, or sunsets, or banana graphs, or whatever. People call these things many different things. And this is the series of what we call train track integrals, in part to distinguish them in contradistinction to the ladder graphs, which are missing these rungs at the top and bottom. And together with Young Hui, we showed that these, or we at least proved one of the cases, and we argued that these would be Calabi-Yaus as well. So this is a Calabi-Yau one-fold elliptic integral. This is a K3. This is a Calabi-Yau threefold, et cetera, goes on forever. And, you know, at this point, you know, at least among my colleagues, I think they saw these examples, my colleagues in the amplitudes business, they saw these examples and they thought, well, maybe we can define our way out of this thing. You know, clearly this thing, at least for massless theories, needs to have 2 massless legs per corner here. So it involves 10 particles, and this one involves 12. And, you know, so maybe if we stuck below 10 particles, we would be free of elliptics. Or if we stuck below 12, we'd be free of these K3 integrals or something. They kept trying to define some category small enough that would be free of these examples. But, you know, the examples, they just keep coming. And we were really interested in Copenhagen. We spent a lot of time looking for examples, and some of them were shockingly easy to find, of things that were less polylogarithmic. and involving fewer particles, and wondering whether or not this need for more external legs could somehow go away. And so the first example we found, we decided to call a tardigrade, and in a paper we called a bestiary of Feynman integral Calabi-Yau geometries. And it was homage to the beautiful book on Calabi-Yaus. This has a K3 in it. Again, it's massless phi-4 theory involving 8 external particles. So that K3 and phi-4, well, it doesn't need to happen. It doesn't need to wait till 8 loops. It happens at 2 loops. It's just that it's a function now of all of the Mandelstams. And that appears already. And in fact, this is actually phenomenologically relevant. It would contribute, for example, at 2 loops to the, glue goes to WWZ at the LHC. This is a graph that would appear there. And unlike this train tracks chain, we were able to construct infinite families of these tardigrades, these fantastic beasts that didn't need to grow in multiplicity. So for even fixed multiplicity of having 8 external particles, or 5 external vertices, where 3 of them are massive, you get a Calabi-Yau